order to get kinetic energy at the bottom, you have to start with potential energy at the top. So, all the work that we put in is equal to the potential energy at the top. So that's a super easy calculation. All right, so in order to calculate our work, it's force times distance for the mechanical energy. And at this spot, this is where all the mechanical energy is equal to 100% potential. Piece of cake, right? Got it? So, number one. Number one on your calculation sheet says, anyway, one says calculate the total energy of the system, and we'll do that potential energy at the top. How are you going to do that? You're going to have to measure the height of the top portion. Well, if your ride is a kilometer long in real life, and it's actually a meter long, what would be a centimeter? A centimeter would be equal to 10 meters. And that's in one of the slides I have up here. So if you measure this and it is, for mine I have, well, let's say 9 centimeters.
90.
The height of my ride is 90 meters.
So we're not calculating our scale model, we're calculating if it was a real life.
Yes, that's a kilometer. So every centimeter is worth 10 meters. Yes.
So if we like do it just flat out, straight, then will it really change like any of the scaling for it? Because like since we don't have the stationer stuff, like where the weights are at.
You'll need to calculate braking.
Oh, okay.
And we'll get to that in a minute, yes.
Wait, that was a kilometer high, or the track's kilometer distance, right?
Your paper says that your track is a kilometer in distance, but you're going to use a 1 meter wire or some string to represent the length of the track.
Okay.
So the scale is 1 centimeter is equal to 10 meters.
Okay, I was like,
Yes.
wow, that was a hard work.
So when we're figuring out how much work is
My riders might die.
so when we figure out how much work is done,
I can't hear you, other people are talking.
so when we figure out how much work is done, we use the force and then like the distance of our roller coaster.
We're just going to go ahead and assume that potential energy is equal to work for now.
Okay.
Because there's some other cool stuff that I want you to calculate. So that's number one. So number two, question two, calculate your potential energy. So you actually calculate question two first. Mass times gravity times height. And I told you in your assignment that your cart and travelers is, how much does it weigh? 45? It's given to you. 45,000 something, right? So that's number two. Potential energy is all at the top there. Number three, ready for three? Why are you filming me? Calculate the power, yes.
So are we making up our mass and height? No, the mass is already given.
Again, for the 20 millionth time, the mass is given to you in the assignment.
Gotcha.
It's on the
And
bottom.
you make your own roller coaster.
It says on the bottom of the paper, it says given.
But
Look
as
at the
Jordan
paper.
pointed out, people
Oh.
might die in my roller coaster because it's really high. The power is work divided by time. So just pick a time value, the time that it will take your chain to pull your
It is.
cart up to the top. And just pick it. Anytime between 40 and 60
It's on
seconds.
Facebook.
You should calculate yours.
Huh?
Why not?
I will, but I didn't have time for yours, period.
Post
I did not
the videos on
have 5 minutes.
Facebook.
I thought you said.
Okay, you pick yours. I will calculate mine
Oh.
moving forward. Okay, so you pick it and you'll calculate your power that you need to plug in your machine with. All right, ready for number 4? Number 4 is tricky. I'm just going to go ahead and assume that 2.3% of the total mechanical energy of your roller coaster is lost due to friction during the entire ride. So 2.3% of your total mechanical energy, once you get to the top of the hill, it's dissipated throughout the ride. So we lose energy due to friction. And I just picked 2.3. It sounds like a reasonable percentage. The rest, and here's your extra credit. If you put a braking station at the end, so I would have a little tunnel here and have a braking station where people get on and off. You need to tell me the impulse that the brakes have to apply to slow down your car to get rid of that last amount of energy. So I have to apply a force and time to slow it down. So we're going to assume that the brakes are going to slow down. Alright, so force tricky. So you got that? How do we do this? What you're going to do is multiply your potential energy, that should be initial potential energy that you got, the entire energy for your system, by 2.3%. This equals the amount of energy that's going to be lost to friction during the entire ride. Then, that's the entire energy lost for the entire ride. Then you get to the fun part. You want to measure the length of your existing ride. So the easiest way to do that, if you have a string or yarn or a piece of fabric, you want to follow the curve. If you have a ruler, you can do this too, but you want to kind of follow the curve with your string, and then follow it all the way around. You want to be quite as accurate as you can. I'm doing it very quickly, because this will give you the actual distance of the track that remains. And then you want to stop it right when it enters your braking station. And then you cut it.
Well, you started at the top of it.
You start at the top. You don't count this part because we're putting work in there. You start right where you let
Your
it go.
potential energy, begins
Yeah.
to when it stops.
So this is the length of the track over which that 2.3% of the friction is stolen. Does that make sense? So now you take that string and you put it on your meter stick and you measure it, and that tells you the length of the track over which 2.3% of your energy is lost. And mine is 89 centimeters or 890 meters.
So we would take like just the mass multiplied by gravity and height, and then multiply that by 0.023, and then divide that by just the distance.
Let's continue on.
Okay.
Okay, so now I know my distance. This can be easily be done by laying a piece of string along the track and then cutting it at the end and placing this against the meter stick. We just did that. Remember, your track is 1 kilometer. That is equal to 1 meter. So 1 centimeter is equal to 10 meters. So 89 centimeters, 890 meters. Divide that 2.3% of the mechanical energy by my length that I measured, and that's my average friction dissipated per meter, which should be for your ride. That's what we want to know. Because you're going to be calculating the mechanical energy at various positions on your ride, and you need to account for how much energy you've lost due to friction. So we want to know the amount of friction lost per meter. So if I start here and I go down into my loop-de-loop and I have all my mechanical energy here, and I want to measure this distance, and I want to know my total ME here, I've lost some due to friction. How much? Well, I measured the length in meters, multiply it times my average, and then I subtract that friction from my ME. So total ME is going to equal kinetic plus potential plus anything lost to friction. So then I want to take a look at what's going on here. When you do your calculations, you're going to know your mass, right? You're going to know gravity. You're always going to measure your height. And just like we did with belly flop Benny, if we know the potential energy and we know the total minus the friction that's gone, we can get to our kinetic energy. Once we know our kinetic energy, we can get the velocity. Good. All right. After we do that, okay, so here's number 4. Number 5. Why do we have to know our velocity at that point? Because I'm asking you to calculate the momentum of your cart at those points that you pick. I believe there are 3 points. So I would like you on your roller coaster